Okay. Normalize the transactions here. Here we go. Okay, so welcome back. Sorry for the delay of 2 minutes. So actually this clock is 6 minutes ahead, or 4 minutes ahead. So actually it's 16:17. So we talked about transactions. So you know all about concurrency, not about concurrency, but about recovery. So you have the transactions and what happens after a system crash. And today it's about how to schedule multiple transactions. So like, you know, if you're using a database system, you have your point of view and you want to use the database, it would belong to you. So you have a transaction, like you have multiple read and write and so on, and finally you commit or abort. Now the idea is, okay, what happens if there's someone else? What happens if there's someone else also want to access the database system? And the idea is always you should compare transactions like your fingers. Like you have your fingers, and normally you have the first transaction, then you have the second one, and so on. This would be the perfect way. And this is called the serial transaction. So the idea is, okay, serialized is safe, but the more users you have, the slower it is. So the idea is, okay, if you have a serial execution, it would be the perfect state, but the problem is you cannot ensure this as long as you want to have more than one user. So the idea is what happens if we have multiple users. And now you see my fingers, and the idea is how can I combine my fingers? That there will be the transaction at the end should look like a serial transaction. So the goal is to have always serial transactions. So you have to get an ordering of the fingers. So at the end there would be a serial execution like the first 10 and then the second 10 or the other way around. And the idea is how can we interleave my fingers, so the transactions, in a way that actually it would be a serial transaction. So that's the whole goal. So what happens if we have more than one transaction? So the first idea would be, okay, we have here two transactions, the first one reading X, the second one writing X, finally committing. So here in between, so today I brought my keyboard with me, so maybe this would be here. Maybe we would read X, so X for example would be 100. Then we would say, okay, we read the value of 100, and then internally the transaction says, okay, we do a plus, for example plus 10, and then we would actually write 110. The other transaction does the same, but actually the transaction here would say, okay, we want subtract, for example, 15. So here we still read the old value. Like here we have the value of 100, we would subtract 15, we only have 15, and we would overwrite the old one. So this phenomenon is called lost update. So this could happen if we do not synchronize our transactions. So this would be the first problem we want to avoid with more than one transaction. The second one would be a dirty read. So here the transaction is doing something. And here you can see, okay, we read that, and finally the transaction 2 aborts. So what does this mean? So normally, what would be the perfect way? The perfect way would be, okay, everything what we read, so like here you have a read of another transaction. So this is important. As soon as there's a write of a transaction T, and then there's another one who reads the same value. So here would be another transaction S. So then we would say this transaction S reads from T. So this is very important if you have more than one transactions. As soon as there's a write of another transaction, then the other one which reads it, and there's no abort in between, then we say, okay, transaction 1 reads from 2. So here we have actually a read of transaction 1 from transaction 2. You see, but what happens? This tuple, this data item, has not been committed. So this actually is dirty. So as long as there's no commit here, so as long as here's no commit, this is missing, here the commit. So as long as there's no commit, this read is called dirty. So this is called a dirty read because actually what could happen, this transaction can abort here, and then actually we should also abort this transaction because maybe there was a money transfer which should not occur. So actually money is gone, but we already booked the money from the other transaction. So this is called a dirty read. And here what can we see? We did a commit, and therefore we cannot abort this transaction, although the original value was wrong. So this is another idea of transactions we would avoid. So this is called a dirty read. So when you use a database system, it should be like you would be the only one. So if you request a value, and if you request the value a second time, it should have the same value, of course, because if you access the data and you did not modify it, then actually it should stay the same, so like in a serial environment. If this is not the case, this is called non-repeatable read. So we see, okay, here the first transaction is doing something with this data item, then again, so we're reading this twice, first and second, but here in between, the transaction 2 is accessing, modifying, and therefore we do not have the same value here. So this is called non-repeatable read. By the way, how would you ensure that the data item is the same? So what idea do you have how to solve this issue? Think of, yes? So you see you have so here transaction 2 is doing something with the value. So for example, we have x is equal 100. So here if we read this value, what's the value of x? It's 100. But here transaction 2 is setting x, for example, to 50. And then if here again we read the value, x isn't 100 anymore, x is 50. So here we can see it's not the same value, but actually we have the atomicity, so like in the acid criteria. It's like, no, it's not the atomicity, it's isolation here, the I, you see. And the I in acid means that if you access the database system, you access it exclusively. So your transaction is isolated, so your transaction does not care about others. Like your transaction is like the only one. So the database system must give you the feeling that you're the only user who uses the database system. So your query, your transaction should be isolated. And isolated means it doesn't matter how often I read a data item. It always has the same value. Like no one else, like you should have the feeling like you're the only user. So the isolation of a transaction. This should mean that it doesn't matter when you access the data should always be the same. And now I ask you as a programmer, how would you solve that you have a data tuple and it's always the same, as long as your program is running? How would you do that? So, like in any programming class, how would you do that when you access a data item that is exclusive access?
I will block it.
How?
So that no other transaction can write on this.
Sure, but how?
For example, constant. Yeah.
No, not with not with constant. Because constant, I think can be never changed. Like it should be like you're the only owner at the moment. Yes.
And make it private?
So?
You can implement a lock.
Yes, exactly. And that's
The lock is released the other to not
exactly, and that's the idea. So I want to show you all the problems, and then I want to show you how the database system is solving these issues. And at the end, I will show you actually it's implemented like locks. And the idea is, so at the end of today, I will show you the different kind of locks. And the idea is, okay, so what you would do here, to avoid non-repeatable read, what we actually would do at the end, would say, okay, I will here have a lock on X, and at the end of the transaction here I have a commit, and then I could release the lock. So free von X. And this would mean that this transaction here would also require to get the lock granted, and as long as it does not get a lock, it must postpone his transaction until the lock is available. So here. So that's actually how to solve that. And you should know the database system does this automatically. So currently we're still discussing the different problems we have, and at the end we have multiple stages. So the more locks we have, the more complicated it gets. Like you have to deal with deadlock detection and so on. And so the idea is, okay, we had before only dirty reads, so we have we need a serial transaction, like a serialization order, for example, but then it gets more complicated. And the idea is, I want to show you all the problems we have, then I want to show you the different schedules, and then I want how to deal with the schedules, and the idea at the end is locking. So non-repeatable read, if you want to avoid that, the idea is, if you want a repeatable read, this means locking. And you can have two kinds of locks. You can have a read-only lock and you can have a write lock. So read-only lock means shared, so that everyone, so it doesn't matter how, if you have a third transaction, for example. Here you have a third one, and if it also wants to read X. So here if it wants to read X, and this one, they do not have a conflict. But as soon as someone wants to write, you need an exclusive lock. So you have two kinds of locks. Only reading, you can allow as multiple transactions who read a data item, but only one who writes it. Okay, so to avoid non-repeatable read, you need locking. Okay, last but not least, you have another problem which you cannot solve with locking, and that's the phantom problem. And the idea is, you just count the number of tuples. And the idea is, okay, like if we would have a lock, like we have, for example, a column of multiple items. So if it would be, so here we have, this is the R table, and we have 1, 2, 3, 4, 1, 2, 3, and we can say, okay, we want to count it, okay? So we can lock this, we could have a shared lock on that, and we can say, okay, count would be equal to 3. But then we insert something into the database. So here, on the right side, here, we insert another element, for example, 4. And then we could say, okay, we count it again, and then instead we have 4 tuples inside. So this, for example, is a problem we cannot solve with locking, and this is called the phantom problem. Okay, so now you have seen 4 different problems that actually violate with the isolation principles of the ACID. And now I want to show you how transactions can be arranged and how this arrangement can help to avoid the problems. So, as I said, the gold standard would be the serial execution. So serial would mean one transaction first, then the second one. This would be heaven. But the problem is it would be slow. So the idea is, okay, at the end, we always want to have the transaction like they would be serial, and this is called serializable. And there's the abbreviation, and the abbreviation is called SR. So all transactions would act like they are serial are called serializable. And how is serializability defined? So, what are the different transactions we have? Like the first one, operations. So every transaction consists of either write or read operations, and finally we have abort or commit. And at the beginning we have the beginning of transaction. Like you remember, like first the transaction 1 first starts, and then it might read an item, it might write an item, and finally it might either commit or abort. Yeah, and actually that's called a transaction. And yeah, and here it's formalized like actually a transaction like contains multiple read or write operations. Finally we have one abort or commit. Yes. And what else is here defined? Of course, abort and commit must be at the end. And for all read and write operations, we need an order. So this is everything. Like I have shown you before, read and write, and at the end either abort or commit. And so as I said, we can just draw it as a graph. So which kind of conflicts do we have? So for every read and write, we need an ordering. So actually it is not of importance which item must be read first, but write, there's always an ordering. Because like this can be, for example, z could be equal to the value of x plus y. And therefore, as soon as we have a write within a transaction, we need an ordering, but reads don't. So reads can be independent, but always the write there's a dependency here, because the write can require the operations done before. Yeah, and I've shown my fingers, and the idea is the idea how to arrange the fingers, this is called the schedule. So if we have more than one transactions, and the idea how to schedule the schedule is called a schedule. And again, what kind of transactions are in a conflict? So as I said, read-read operations never cause a conflict. So here, read-read is never a problem. But as soon as there's one write transaction, we have a conflict, and we have to define an order for the schedule. Hello. Okay, and now the idea is we can also formally define. So actually what we now do is like we have two transactions, T1 and T2, and like we have a read transaction here, read and write, and finally commit, and here we have also read and write and commit. And now we want to serialize this. So we want to say, okay, we have first read x von 1, then write x of 2. Then we would have for example, the second transaction, writing x, and finally we have the commits. And that's the schedule we have, one exemplary schedule. And then the idea is, okay, what are the conflicts? And the conflicts, of course, are always when a write is incurred. So here we have a write, so we know, of course, the write must happen after the read. Then we have another one. Here write always incurs a conflict with read, so we have another conflict here, another one, and so on. So these are all the conflicts, and therefore this must be the schedule, and we cannot rearrange the operations so that we have the same value. Okay, so what you have seen here, like this ordering, and this we can formally define an ordering, and the idea is, okay, we have all the operations, and then we have more than one transaction, and for all conflicting operations, so all the read and writes, there we must have an ordering for all the conflicting operations. So what I have shown you with the ordering symbol, that's all. So as soon as there's a write, we need an ordering. Yes.
In the previous example, you showed when we execute write 1 and then we do write 2 and then commit 1. So wouldn't the value of write 1 be overwritten by write 2?
Yes. So like, but yes, sure. But yeah, so you mean because as said here, write 1, write, then we had this next one. Yeah, of course, here it would be overwritten, sure. But it's fine, for example, if you have two transactions, like if it would be like T1 is adding a value and T2 is using the value, like x minus 50. It's a bank account, you have the money. For example, you earned it because you're working as a student assistant, and then you want to go eating an ice cream and you want to spend the money, so that's fine. As soon as it's really yours, like it's not a dirty read. And you can see that it's not a dirty read because of the commit here. So the problem would be actually, and now we all, so actually these are the problems I want to show you. What happens now if this, so this is the ice cream you want. So like this is the ice cream, you here, ice cream. And this, for example, this is the money you get for working as a student assistant. So what happens, okay, if you already spent the money for the ice cream, but then actually the university has no money because it's bankrupt, we don't know, and then we can say, okay, instead of a commit, there would be an abort of the transaction. And this would be the problem, because then actually, if you don't get the money from the university, then you cannot buy you an ice cream. And therefore actually, what should happen if there's an abort of the first transaction, you also should abort the second one. And that's the problem we have. So, yeah, and actually that's what we want to solve. And that's why I want to show you what kind of operations are allowed. So this is what we discuss in the next slides. But of course, it's overwritten, but it's fine, because it's a transaction. Okay. So now it's just about the conflicting operations here. And as I said, if we have a schedule, and let's assume we have 3 transactions, and now let's have these 3 transactions. Like T1, no, T2 is the first one, T3, and T1. Okay, so let's make a serial schedule. Where should we start? Which is our first one? What? Read 1. Okay, we can take it. So the first one, so we can always pick an item there's no error pointing to. So here's no error pointing to, so we can use it, R1. Fine, what do we take next? We can take it, yes. And next? Who said what? Committed. We can take everything. We can also take R3. We're not allowed, but the only thing we're not allowed to take is W3. So we can take whatever we want. But you want to pick committed 1. Okay, it's fine. It's fine. But we could also have picked R3. So what to pick next? Write 3. Yeah, we do not have a choice. Yes. So now we have a choice. So we can either take so read 2 or write 2. Now we have again the choice. So we would have again the choice between those two. And then we would have again the choice. Again. And finally, we can pick one of the 2 commits. Okay, so this would be one serialization order of 3 transactions. So if you want once to serialize, that's how to proceed. Just take the one without an arrow pointing to, and you got your serialization. Okay, but is this the only serialization order we would have? No, because like it's always the same. We could sometimes choose between two, and now that's what we want to define. If there's different serialization orders which lead to the same result, the schedule is called conflict equivalent. Yeah. And how is conflict equivalency defined? Defined as soon as you can change two non-conflicting operations and you still have the same result, then two schedules are conflict equivalent. So I have an example for that. So here we have again one schedule, only with two transactions. So actually only two. So T1, T2, we have a read X, we have a write of Y, and the second one is reading Z and writing Y. So what are the conflicting operations? Writes on the same data item.
Writes on Y.
Exactly. So this is the only conflicting operation. Okay, so as long as we don't change both, the new schedule is conflict equivalent. So like this is the first one, and now we can rearrange. For example, we can swap those two. Both are not in a conflict, and we get this schedule. So this schedule is equivalent to the first one, conflict equivalent. Then again we can swap, for example, commit 1 and write 2, because like this is the commit of another transaction, so we are allowed to swap those. So we still have the same history, the same schedule. But those two, are in a conflict, those operations, and therefore the new schedule is not conflict equivalent to the first one. So that's how you achieve conflict equivalency. Changing non-conflicting operations. Okay, so I talked about the idea of serial transaction, and as long as you can so if you can change it until you have a serial order, it's called serializability. So can we change it to a serial order? So where the commits here and here. Now the idea is okay, maybe take the other one. Yeah, so let's prune everything, and let's say, okay, we want to move the commit. Like here we would move the commit one left, so then we would have the same order, the same schedule, but within a different order. We have write, commit 1, and then we would have the read of Z and the write of Y. And you see, we have first all the ones, and then we would have all the twos, so all the operations of transaction 2. So this would mean this would be a serial order, okay? And if you can make a schedule serial, it's serializable. So here, this is the definition of serializability. And as I said, this would be the perfect state, because like if you would have a serial execution, it would be the isolation to everyone, and this is actually what databases want to have. So we only allow serializability schedules. Yeah, and here again a definition. So a schedule is serializable if there's one schedule that is actually serial. So what I have shown you, if you can transfer the operations, if you can swap the operations until you have a serial schedule, then the schedule is serializable. So that's actually the definition of serializability. Okay, so you can do it by swapping it, and there's another more easy way to check it. And actually that's a serializability graph. And the idea is, okay, how should I draw it the best? So the idea is, okay, do I have white here? Let's see. No, I don't. I don't want you to see the errors. Okay, so this the idea is, okay, as soon, yes?
I just used the whole concept from like 3 or 4 slides ago. We were just changing the places of the reading and writing, and I didn't get what happened there. And we are going so fast, I really don't understand what's going on.
What's your question? So
Just like 3 or 4 slides ago. We were just changing the place of these comments. Is it coming from the last slide we had here, or is just a new order? I didn't get that.
so which order? So we
These ones, we just changing the comments and reading and writing.
So we still have the same operations, but we just swap the positions of the operations. And the idea is, okay, we want to swap it until we have a serial execution. So the idea is, the numbers here stand for the transaction itself. So like, you have transaction 1 and transaction 2. And like you have a read X and you have a write. And here you have also a read and a write. Finally you commit. And now the idea is you have the conflicting operation, that would be the writes, and every operation except the conflicting operations, you can swap the positions. And I have just shown you how you can come from the first schedule to the second one and to the third one. And actually the last one would be the conflicting operations here, and therefore the last one is not equivalent to the others. That's everything. I want to show you serializability. And the idea is, okay, like here we have our schedule, and then we have all conflicting operations, and conflicting operations, as I said, is as soon as there's one write operation involved. So on the same data item. So would be the same. So I start always by writing it down. I have my first transaction, I have my second one, and I have my third one. So I start, okay, I have a write of X, my write of Y, and then I have to commit. Then I would have to read of X, then I would have to read of Y, and then I would have to write of X and commit, and then there's another write of Y, and then I have another commit. Okay, so what are the conflicting operations? So here I see the X, and here I see the X, and here I see the X. Okay, so here's the first conflict, and then the second conflict would be the Y, and here would be the Y, and here again would be the Y. Okay, and now the idea is, okay, I write down all my transactions, T1, T2, T3, and then I can add the errors. Like I have the first one, dependency, T1 must come before T2, because the write of X must occur before transaction 2 reads it. So, okay, this is the first error here. This is the red one. And then there's the second conflict, like the write of Y must happen before transaction 3 reads it. So this must happen before, and therefore this is the second error. Okay, so this is the serializability graph. So SG is a serializability graph. And if the serializability graph is acyclic, then it's serializable. That's all. And then there must exist one schedule which is serial and which would come to the same result. So then you could change all the operations to come to a serial execution. Okay, so first property, serializability. Okay, and what would be the serialization orders here? So, as I said, like we now know the fingers I have, there would be one order for the 3 transactions in one way, or more than one way. Which would be the first transaction that must happen? No. T1, of course, because we can, like also in getting the topological ordering, always by taking one, there's no error pointing to. So there's no error pointing to, so we can take T1. Okay, so we take this one. We can also then remove those 2 errors. So what could we pick next? For example, yes. And then T3. Now the question is, could we have done it differently? Yes. And it would be T1, T3, T2. So those 2 execution orders would be equal. So this is called topological ordering. Okay. So again, we have 2 different possibility schedules, and both schedules are equivalent.
Could you move back to the last slide?
Yes.
Well, so we have the conflicts in both T1 and T2, in T2 and T2, right?
The operations in T1 and T2 and T3, yes.
And still, we started with T1, went to T2 and T3, or T3 and T2. So how the conflict is gone?
So the question was whether the conflict is gone.
Yeah.
So like the conflict always exists,
Okay.
but it's like we need to find an ordering.
Okay.
And like the idea is, okay, so currently it's not about eliminate conflicts. So it's
Okay.
good to have to
Okay.
know an ordering.
Okay.
And now the idea is, do we want to allow every kind of ordering, or is there certain classes we want to allow?
Okay, still with the ordering that you did in this slide, we still have the conflicts.
Yeah, of course. We always have
Okay.
conflicts. Like we have, as soon as there's a right, you have a conflict. And as soon as you have a right, there must be an ordering.
Okay.
Yes. And now the idea is, okay, but when is it allowed to read something which has been written? And this, now we want to classify. So it's important. So the first one is we have the conflicts for this serializability. So we should know what transaction must come first. And then second, we also want to know which transaction reads a value from another one. So we have 2 kinds, like we have conflicts. A conflict is always with regard to write. So where is it? So here this is the definition of conflict. As soon as there's a write, this is a conflict with regard to serializability. And then we must have a certain schedule. Maybe there's one transaction which must come first before the second. Like we have the dependency. So actually a conflict means a dependency between 2 transactions. Okay. So here I have another example. And now the idea is, okay, this wouldn't be a serial order. There wouldn't be a serial order possible. Like, we have x, 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 and here we have y. So you see, okay, we know that the write on the transaction 1 must come before transaction 3 reads it. We can also, so I really loved to draw it down, because then it makes something more clearer to me. So like T1, T2, T3, and like we have to read of x, we have to write of x. Okay, now so the write of x, then we have to write of y. Okay, so then what could come next? Then we could have to read 3. Then what could come next? Then there must be the read of 2. And what could come next? The write would come next. And then the write of x again would come next. And then we could have the commit, here the commit, here the commit, doesn't matter in which order. Okay. So what are the conflicts? So we see that the read of transaction 1 must come before transaction 2. So like this would be the first one, T1 before T2. Is it the case? No, it isn't. No, it isn't. So what are dependencies? Oh yes, indeed, indeed. Yeah. So we have the first dependency like T1 before T2. Is it? Okay, so let's have a look. So we have T1 before T3, because we have to write before, yeah, of course, T1 before T3, yeah, sure. This is this one. Then we have T2 must come before T3 and T1. T2 now. This would be the second one. And regarding the y, we only have 2 before 1. So again, we have another dependency. But actually, there would be also a serial order possible. Is it really the case? What about x3 and T2? Okay, yeah, of course. Because we could move T2 downwards. What we could do is, so this was a bad example, because what we can do is, no, sorry. We could move this one downwards here. There's no conflicting operation. And then we would have T1, T2, T3. Yes. This would be the only topological ordering here. Actually, I wanted to show you a cycle, but this is a schedule which is serializable. Okay. Let's have a simple example which is not serializable. And this would be this one. So, like we have to read 2, which happens before 1. So again, T1 and T2. Like we have first to read 2. Then we have to write of x. Then, sorry, first the read, then the write. Then it doesn't matter what comes first. No, it does. We have to write of y. And then we would have to write of 2. And finally we have a commit. And therefore you see we have the first conflict on x and we have the second conflict on y. And therefore this must come exactly, it be interleaved like that. And therefore we have a cycle in between, and as soon as we have a cycle, the execution order cannot be serialized anymore. So here the serialization graph is acyclic, and therefore there's no serial schedule. Okay, so now you know everything about serializability, and that it means that write operations have conflicts if they are accessing the same data item, and this is important with regard to serializability. And now there are different kinds of properties, and this is with regard to reading. So if there's an operation, a transaction has a write operation, and another transaction has a read operation, then the transaction reads from the other. And this is with regard to, and the three properties are called recoverability, avoiding cascading aborts, and strictness. And recoverability would be like if you remember the ice cream example. Like you have two transactions. The first one, like you get the money, and then you afterwards suddenly you want to spend the money. So you're buying yourself an ice cream. You commit it, but actually then the university is bankrupt and you do not get the money actually. And this is the kind of transactions you want to avoid, because like the money is already spent, but actually it was never yours. And to avoid this, you want to have recoverability. And this actually means if as soon as there's an abort, all the transactions who read the value should also be aborted. So I said a transaction reads from another transaction as one wrote it, the data item. There's no abort in between. So the abort here, so the abort here, if it would happen here, you never would have had the money. So if this is not the case, you have the money, and then so you read it. So the transaction here has not been rolled. There was no rollback of this transaction. So the data was persisted, and then you read it, and so yeah, transaction 1 wrote, transaction 2 reads the data item. Okay, and now actually the idea is, before you commit here, you should know whether the money you received or not. So this means before transaction 2, who reads the value from transaction 1, is allowed to commit, there must be a commit of the other transaction before. So here, beforehand, there must be a commit, because then you are allowed to spend the money. Because what happens if if there's no commit but an abort, this means that you must cascade the abort. So this would mean that, okay, here's the abort, then everything which has read from my transaction, so this transaction 2 must abort all the values. So this has all been reset. So this is nonsense, this is nonsense, and then we can undo all the operations, the single. And this is called recoverability. So as soon as there's a transaction, then this means, okay, as soon as the transaction reads from another one, the other transaction has to commit it before. This is called recoverability. And when you do that, the abort here, you abort it, and then you cascade the abort to all transactions that have read. So actually that's the two things I want to explain for today. The first one is serializability, and the second one is recoverability, and all the other things which come with cascading aborts, and how you can schedule, what kind of schedules you want to have. So like serializability is the one kind of property, and the other one is with regard to recovering transaction. So all the things we have here, like recoverability means, okay, as soon as another transaction commits, there must be an abort or commit of the transaction who wrote the value, and then if you want to avoid that this transaction is allowed to commit or not. If this transaction has to cascade the abort, then this means, okay, instead of here, the commit must happen before. So if the commit is here, then you would avoid cascading aborts. So simple. Okay, so let's formalize it a bit. So the relationship, reads from relationship, as soon we have two transactions. The first one writes the transaction, so here Tj writes the transaction and Ti reads it. So this means that there's a write and afterwards there's a read, and the transaction who wrote the data did not abort, and so this the value is still persisted or still exists. And what also is important to the read from relationship, there must not be a write in between, because if there would have been a second transaction who overwrote the data in between, then of course you read the data item from the transaction who last wrote the data item. Okay, so this is the reads from relationship. So quite simple, you have a write and afterwards you have a read. And now remember the ice cream example, you get the money from one place and you will spend it to another one, and this means, okay, a schedule is recoverable if you read the data from another transaction, then the other transaction must have committed. Quite simple. And why do you need it? Of course, because like it must be consistent. So money you never should have is not so it would be a bad idea if suddenly there's money coming from nothing, and also like it would be the C and the D, so consistency and durability. So non-recoverable schedules would violate consistency and durability of databases. Okay, here's an example, like the ice cream example I've shown. Like you have two transactions. The first one writes the data, the second one reads it. Then the second one writes another tuple and wants to commit it, but actually the first one aborts it. And then actually the second transaction should also be undone, but it's not possible because here already the commit occurred. How can you solve this? How can you make this schedule recoverable?
The commit is only allowed for the transaction 2. If there was a commit
Exactly.
for transaction 1.
So where should we place the abort? Quite easy. It would be sufficient if you just would place it before the commit. Then it would be recoverable. Okay, so first property, recoverability. So now what happens? If we have, so this is a recoverable schedule. Like for example, this would be you getting your money as student assistant or research associate. You get the money. You get, for example, what do you earn? Let's assume 1,000 euro. Okay, so then we would say, okay, you get the money and there's another transaction, maybe your friends, your husband, your wife, he or she says, now let's spend it for example, I want to have a nice race car. So let's say, okay, I want to spend it for 1,000 euro, you do not get much, but then, okay, you take the money, then there was another one, maybe the children, they also want to have some nice games, whoever knows, and they are all spending the money. So then, okay, suddenly the university gets bankrupt and you say, okay, unfortunately, this must be this transaction, so my income must be undone. What does this mean? So we see everyone who has read it. Okay, so it's like made a mistake, like the idea is we have different accounts, so it would be like you get the money. Then it would be, okay, like your wife, your husband buys a race car. Then the race car owner says, okay, now he got the money and now he buys maybe a holiday. And then he spends the money he gets for the holidays. and then he's living on an island and he wants to have some fun and maybe for getting some dinner there he also spends the money and so on. But now the transaction 1, so your income, aborts. And this means, okay, we need to make everything undone. So this means you don't get the money. This means your family doesn't get the money, so the race car owner never gets the money and the race car owner never could go to holiday. So we must undo everything. Like we have to first undo this read transaction, this write and read, and so on. Because like there's a dependency of y, then there's a bit dependency of z, and finally of v, and of course of x. And this is unlucky. So the idea is, okay, we want to avoid this. And how could you avoid this? Yeah. You should? Yes, exactly. So the idea is, if one reads the data, there must be, so if there's a transaction who reads the data, this means there must be the commit before. So if we move the abort or the commit a few steps above, so here there's the abort or the commit, then we would have avoided the whole problem. And this is the definition of avoiding cascading aborts. As soon as there's one transaction reading from another, then the commit must happen before the other transaction reads it. So before this transaction reads it, there must be a commit. Before this transaction reads it, there must be a commit, and so on. And then the schedule avoids cascading aborts. Okay, and we can even make the rule a bit more harder, and not only avoiding cascading abort, but strict. And strict means as soon there's a write operation. So it does not matter whether read or write. So as soon as there's conflicting operation, not only a write operation, and then there must be a commit before. So so already when there are two writes. So if like we have two transactions again, and the first one writes the data, the second one writes it, and then we have to commit here and then the commit here. So this would avoid cascading aborts because we never read the data item here. So there's no read of x. So there's no read of x. So if this does not happen, then this would be, the schedule would be avoiding cascading aborts, but it wouldn't be strict. And therefore we can make it more sharper, and we can say, okay, more stronger is the correct word. We can make the rule stronger, so if there's any operation regarding a write operation, there must be the commit beforehand, and then we call the schedule strict. And why do we need it? Because for physical logging, so remember physical and logical logging. Logical means just having the differences to the old value, but if we want to allow physical logging, just storing the old value, then we need strict schedules. Okay. So you remember all the properties we have. We have recoverability, we have avoiding cascading aborts, and we have strict, and we have serial histories. So what's the relationship of these properties? So if we have a strict schedule, is the schedule also avoiding cascading aborts? Why not? So the other way it is. So if we have recoverable, so all the so like we made the rule stronger. So like cascading aborts means if one transaction reads from another, then the commit must happen before the read. And now, if it either reads or writes, then there must be a commit before. So the rule for strict is stronger than the one for avoiding cascading aborts. So we know that if a rule is strict, then if a schedule is strict, then we know that it's also avoiding cascading aborts, of course. So we know as soon as one schedule is avoiding cascading aborts, we know that it is also strict. And also the other way, like if a schedule is recoverable, so of course, because like if we have a cascading abort, this means we had a recoverable schedule, then this is also, as soon as we are avoiding cascading aborts, the schedule is also recoverable. And of course, if we have a serial history, then a serial is like the best thing. Serial is always strict and always avoiding cascading aborts, and of course it's also recoverable. So we can draw a Venn diagram. So like we have, do I have somewhere? So we could have, okay, we have the serial transactions. We have the serial transactions. Then we have the strict transactions. Then we would have the transactions that are avoiding cascading aborts. And recoverable. Oh, I made a mistake. This should be the same, so sorry. Of course it must be missed. So of course. So okay. So that's the Venn diagram. So, and you remember what else do we have as property for schedules? So now we have all with regard to read-write. So we have defined the reads from relationship, and before we have defined serializability. And where do we put serializability inside of this Venn diagram? Of course, all serial schedules are also serializable, of course. But like, there's an intersect. There can be recoverable schedules that are serial, but they can also be non-serializable. So here we have serializability. And now the idea is, okay, what we want to have at the end is, we want to have the intersection of the strict and of the serializability schedules. That's our goal. Because strict, because of the physical logging, of course everything should be recoverable. And so the idea is getting all the strict and serializable schedules. Okay, so here you see again the classification, like you have the serializability, you have the serial schedules, and you have all the other kind of schedules. And we have, I think, this refers to the histories defined before. Okay. And now the idea is, how can we implement them? And as I said, the idea would be with logs, and inside of the database system there's the scheduler. The scheduler gets all the database queries, and now the idea is, okay, when to do it. And there are two strategies. The first one is pessimistic. Pessimistic means claiming all the logs beforehand. First I want to have all my logs, and then I'm doing the things. And optimistic means, okay, I just do whatever I want to, and at the end, I check whether my write set is in a conflict with another write set. So optimistic means afterwards I check for someone else also modified the same data items, and pessimistic means locking. So pessimistic is always equal to locking. Pessimistic is always equal to locks. Okay. We all now discuss it. Yeah. So we need to save queue. Yeah, as I said, pessimistic always means locking. And the other idea is, okay, optimistic. And optimistic is in the first means that I can do it immediately, but then this might incur a rollback afterwards. And one idea would be using timestamps, and another idea would be using comparing read and write sets. But this is up to next week. Okay, so today I want to show you logs. And the idea is, okay, I've shown you all the single items like reading A, reading B, and reading X, reading Y, reading Z. And the idea is, okay, now assume that every data item has one log. And before we can access it, we must acquire the log. And if someone else has the log, the other transaction must release the log. And now the idea is, how can we use locking to gain serializability? And the idea is, now I want to show you two-phase locking. But the first, as I said, we have two kinds of logs. Like the first one is shared, and shared means only reading. And we can have as many reading transactions as possible. And X means writing. And at every time only one transaction is allowed to write. So here you have shared. Shared means reading, and X means writing, exclusive. And you of course see that shared logs are compatible, of course, with shared logs. But if you want to claim an exclusive log, there must not exist another log on this data item. Okay. So now the idea is two-phase locking. And the idea is I have two phases. I have a growing phase and I have a shrinking phase. And now the idea is, okay, in my growing phase, I'm getting all the logs. And at the shrinking phase, I'm releasing all my logs. And yeah, like here you see, like we have a transaction. And for example, what do we have? Transaction. We have, for example, we have a write of X, read of Y, and we have a write of Y. So this means, okay, we need to gain logs on X and Y. So here we can lock, and here we can lock, and here we can release. Yeah, it's quite easy, two phases. So let's have an example. So here, again the growing phase. So the first is we need here the log of X. So we have the log of X, so an exclusive log on X. Then we have an exclusive log on Y. And this is the growing phase. And then there's the point of no return. And as soon as we have, so maybe I should have drawn an x-axis. So this was at time 2, and this was at time 7. And here, point 9 is the point of no return. No return. and so here 9. And afterwards here I release the first lock, and then I'm not allowed to acquire any other lock. Like I have the unlock and I have of X and then the unlock of Y. Okay, in the meantime I have my shared lock of X, but as I see we have to wait. We have to await until the first lock here is achieved, is released. So here we can start with T2 after step 9. So here I can lock, acquire a shared lock on X, so the first one, and then I can acquire the second lock on Y, so a shared lock on Y, and then for transaction 2 the point of no return starts at 16. So here at 16 is the point of no return for the second one, and then it releases the locks. Okay. And the idea is, okay, 2PL ensures serializability. So 2PL means if there's a schedule which follows 2PL, we can assume first serializability, and we can assume that we only have recoverable schedules. So from 2PL we know it's serializable and recoverable. But the problem is we don't have if we do not ensure we do not avoid cascading aborts, because now if what would happen if here would be an abort here, if transaction 1 would abort here, and we see that here we have a read dependency. Transaction 2 reads from transaction 1 the X here. So we know, okay, inside of this shrinking phase, as there's no so the shrinking phase is a phase and does not incur suddenly. So we have really a phase. This means, okay, we release the lock step by step, so the other transaction can start, and therefore the other transaction might already read from the other transaction. This means this 2PL does not ensure avoiding cascading aborts. So here an abort would mean we would have to abort all the transactions that read here. Yeah. Okay. How can we ensure avoiding cascading aborts? Regarding the logs. So it's just about the logs. So yes, it's with regard to the commits, but the logs.
The unlocks should be done directly before the commit.
Yes. So the idea is, okay, the unlocks and the commits must happen at the same place. So suddenly, at the same time, not at the same place, at the same time. So the idea is, okay, until the end of the transaction we hold all the locks, but then if we do it everything at the same time, so commit is done at the same time as we unlock, and then we can avoid cascading aborts. And this would be the strict two-phase lock. Okay. So today I wanted to end by two-phase lock. Yes, question please.
Last part, when we want to write commit at the same time with the unlocking the variables, does it? It's like we are doing the first transaction and then we are starting the second.
I'll show you here with the example. So this would be concurrency which adheres to the two-phase locking. But now the idea is, okay, everything must happen at the same place. So, so the idea is, okay, the first thing what would have changed is unlock both unlocks must happen at the same time like the commits. So this would mean, okay, the write must happen beforehand. So we would have the write here and not the unlock. Then we could have the unlock of x down here, so it doesn't matter because it's an atomic operation. So we would have the unlock of x here, and this would be atomic. So all these operations, unlock of both would be atomic. Okay, so what would this mean to transaction 2? So if the unlock of x happens here in step 14, transaction 2 cannot acquire the lock in step 6. So the lock can be acquired here. So we would have to move the lock down here, and then we would have to move everything. We would have to move the read here, and also acquiring the lock of y, the shared lock. Okay, this would be at the same time because it's always dependent from here, because we waited here anyway. So this would mean, okay, to commit the read of x would happen after the commit here. So we would have the transaction 2 actually would start after step 15. So here transaction 2 would here acquire the lock of x, would read x, would acquire the lock for y, and would read y.
This would be the serial version of this two transactions, wouldn't it be?
Yes, it would.
That means for this case, our 2PL locking is not better than the serial.
In this case, yes. Yeah. Yeah, it would be interesting to get what would be, yeah, to get a schedule which would adhere to the strict 2PL protocol and is not serial. Yes. Yeah. Indeed. Yeah. If we move the unlocking at the end, how can we assure that the abort doesn't happen when? So
abort, instead of the commit in transaction 1 means it unlocks the x and y.
yeah, of course.
Instead of the commit, there's an abort.
If here would be an abort, yes. And so it's not about one transaction whether it aborts or not. That's not what we're discussing. It's about what happens to other transactions. So what happens, like if another transaction reads a value and the other transaction aborts, then we also have to do, the other transaction who read the value also needs to abort. We need to roll back the other transaction. That's the problem. And by avoiding cascading abort, we are avoiding that the other transaction has to do a cascading abort. So like the problem would be, it doesn't matter now whether this aborts or not, but in the original case here, an abort here would mean that every value that transaction 2 read from T1 must be undone. So here the read of x, because this was a dirty value, this was a dirty read, because it was not committed here. So if here's an abort, then we have to undo this transaction, and this should be avoided, and that's the idea. So the relationship with other transactions. And if it happens at the same time, unlock and abort, then this would mean, of course, if here's an abort, we would undo this transaction before the other transaction starts. And of course, because I was thinking about what other transaction might exist, it would be interesting if two transactions read the same value but are writing two different values. And then we would not have a strict schedule. Because I was thinking about what would happen. So if we would have, for example, two transactions, two transactions, and if they are reading different values, like if they are reading x, this is reading x, and now what else could happen? Just thinking of a non-strict schedule which adheres to strict 2PL. So can we have a write somewhere? We can have, of course, a write of another, but here we need a shared lock, and we could have, for example, here write of y. Then we could here have a write of x, commit. And here we could have, yes, this should be possible with strict 2PL, but it won't be serial. Yes. Because like here, we first have a shared lock on x, then we have, this also acquires a shared lock on x. Then we want to have here, so if we have the locks here, like shared lock s on x, shared lock on x, then we need here an exclusive lock on x. So we will have to wait until T1 releases its shared lock. So here we have an exclusive lock on y, and then here we release all the locks, and then here we would have, then we could acquire the lock. Yes, exactly. And this would be an example for a non-strict schedule under strict 2PL. So it's just regard of writing the same value. And of course, that's actually the strictness. If there's a write, then the commit must happen afterwards. Yeah, and actually that's what we want to have. Strict. Yeah. Strict 2PL ensures strictness. Yes. So if we have strict 2PL, this means so if we have the strict 2PL, then we have serializability and strict. And 2PL only means serializability and recoverability. Yes. Okay, so the idea is that we would do a tutorial afterwards, and the idea is to make now a break. How long? 15 minutes? So, sorry? We do 15 minutes. So until this clock is 6, so actually 5 before 6 we meet again. 15 minutes of break.